this will happen. This will happen, we know that when you increase the number of sub-intervals. So how do we define this Riemann integral? So we define this to be the limit of this series actually. So if this series is convergent and the limit of this series exists, that limit is basically the value of the function. So that's how we define what is called Riemann integration. Now, so that's calculus 1. Okay. Let's go a little bit ahead. How to define the integral from a to b, okay, of a function, say, e with respect to
GST.
So what should be the assumptions of g of t? Remember? So it must be monotonic, okay, and it must be bounded actually. Okay, so it must be monotonic and increasing and decreasing. Okay. Then such a notion kind of makes sense. And how do you define it? So you, with the same notation, you say that if this limit exists, okay, so limit delta n goes to 0, or the log of delta n goes to 0, okay, and this sum I equal to 1 to n of f of I multiplied by g of pi minus g of pi minus 1. In other words, the increments of these functions, g's are. Okay. So the increment of these functions, g's. Now, this guy makes sense if this series is convergent. Okay? If this series is convergent. Now the question is, for what kind of functions g such a series is always going to converge? And that's a very interesting question actually. Okay? Maybe someone can also give a funny answer. Can say, okay, if I want to define a to b, say f of t dg of t, I can use integration by parts. Okay, f of t g of t, and going from a to b minus taking the, so they say, g of t from a to b and df of t, but this is not solving the problem because we are defining, expressing integral downward. We want to still use integral in the problem we want. Alright, so we want to make sense that this phenomena of this species works for what kind of the g's. In other words, what properties f and g must have so that this series is convergent and this integral makes sense. Okay? We are interested in. So, what would be the most obvious case of g? So, if you have f and you want to integrate it with respect to some function, what would be the most obvious function that you want to integrate with respect to? Huh? Also, not that obvious. So I have a function f and I want to integrate it with respect to some function. Give me that function. Are the easiest choice of that
g of t to be t.
I'm sorry?
G of t to be equal to t. That's Riemann straight line.
Okay.
Integrating f.
But that means if you take g of t to t, then we are talking about
Riemann integration.
F with respect to f and
let's try to integrate a function with respect to itself. Forget about some other function. Let's try to integrate some function with respect to itself. Let's see what happens. So here is the question that imagine f is continuous on A to B. Question is, can I define the integral of f of t with respect to itself? Let's see what we got. With this notation, let me define something called ln. And ln is, so how are you going to define it? So, roughly I want to define it in the terms of this partial sum, and then I want to take the limit of the partial sum. Okay. So let's have this what we call roughly the lower Riemann sum. Not lower Riemann sum, but the Riemann sum, right? That Riemann sum, but where the f is evaluated at less than 1. Okay. So consider this I equal to 1 to n f of pi minus 1 and pi minus and by Rn, I just go to n f of pi minus f of okay. What would be the difference Rn minus Ln? So this is going to be this minus this, which is this sum minus this, meaning this minus this. You can take this away by distributive law, so you're going to get a square of this. You're going to have a sum I equal to 1 to n f of pi minus f of pi minus 1. Subtract and distributive property that is. Basically, what I want to do, I want to compute explicitly the value of ln and Rn. If I have one value, which is written in big abstract manner, but I want to have a more complete value if I want. So the next thing is add that. Okay, so Rn plus ln. What do you think we're going to get? So you're going to get difference of the square I equal to n f of pi minus f of pi minus 1 squares and squares. And that's a telescopic sum. Square of b minus f square. Look, f is square. Yes, b square minus f. Now, if I treat this 1 and 2 as a system of equation, okay, in ln and Rn, so I can solve it for ln and Rn. So if I solve it, I'm going to get Rn to be 1 half of f of e squared minus f of a squared plus I equal to 1 to n. Okay.
f of pi
F of pi minus
f of pi minus 1 square.
f of pi minus 1 square. You have it. How about ln? 1 half f of e squared minus f of a squared minus I equal to 1 to n f of pi. Let's start from here that pi minus 1 is square. Okay. Now I want to say take the limit of delta n goes to 0. So you're going to get.
Difference 0.
If this limit exists for any choice of your point actually, then these two expressions must be equal to each other. Okay? These two expressions should give you, otherwise these two both sums should give you the same answer. But the answer is, are you going to get the same answer? Yes, is not equal to R. Not going to get it. Okay, okay. This ln is not going to Rn. These are two. Here you are adding and here you are subtracting number. So if the limit exists, you should have equality, but it doesn't. So what does this mean? This means, forget about defining the Riemann Stieltjes, integral of a Riemann Stieltjes, integral of a continuous function with respect to it. So forget about defining the integral of a function with respect to a noise or a random function. Okay, you are not even able to define the integral of a continuous function with respect to itself. With respect to itself, you can't even have it. Forget about defining the integrating with respect to some random phenomena in Riemann Stieltjes sense. You can't do it. Okay, unless this f has some kind of properties. For example, what property you would like to have in f so that these two become C? What property you would like to have in f so that these two become equal? These two would be equal. One of the possibility would be that if these two expressions go to 0. In other words, if this goes to 0, this goes to 0, then these two are equal. In other words, if a function f has what you call the quadratic variations along with continuity, quadratic variations along with continuity, then you can give a sense to this kind of an integral. Okay? You can't just take any function and integrate that function with respect to either function. Okay? The functions should be nicely and cleverly chosen. So in other words, Riemann Stieltjes is even a trouble. You can't define it unless your f, define it f with respect to itself, actually, integral of f with respect to itself, until and unless f has certain properties. Okay? In other words, Riemann Stieltjes is not a good choice. Okay? Riemann Stieltjes is not a good choice. It's not. Saying that, okay, just define integral of b with respect to the randomness dw is, it's not a interesting choice. Okay? So what does this simple example shown? That a Riemann Stieltjes integral is not a sophisticated, tool to define the integral. One of the answers could be that, okay, if these guys should go to 0 for the function f, in other words, it has quadratic variations, then the integral makes sense. Another condition under which this integral is going to make sense, in other words, the integral of f with respect to f is going to make sense if you have differentiability. If you have differentiability. So next, another example could be that imagine f is a C1 class function. Okay? F is C1 class function. So it's a continuously differentiable function. Okay? then what would be the difference between Rn minus Ln? Or it's absolute? So it's going to be equal to, it's going to be equal to I equal to n, okay? F of Ti minus F of Ti minus 1 square. Okay? But on the interval Ti, so this is C1 class on the entire interval A to B now. There will be the open interval A. So this function is it's continuous and differentiable on A to B, so it is also continuous and differentiable on each subinterval, isn't it? So you have something called the mean value theorem, which tells you that if you have such kind of a function, you can find, P star I in the interval Ti minus 1 to Ti such that what happens?
Derivative.
That the derivative of function at this point is equal to
Average
equal to what?
of
The average of f of Ti minus f of Ti minus 1. Okay, so
divide by Ti.
I can multiply this. Okay, so I can multiply this. So once I have this, I can rewrite this expression as I minus ln equal to sum of I equal to 1 to n. And I say that this would be f prime of Ti star times f of Ti minus f of Ti minus. Would you be happy with this? So you have a square here, so one expression I'm just replacing it by this actually. So I need to obviously have Ti and Ti minus. That's it. ठीक है जी? Does it make sense? No. So just square it. Square it and Ti and Ti minus 1 square. Okay. I can estimate this by some I equal to 1 to n, the infinity norm of prime and its square times Ti minus Ti minus. Remember the infinity norm? So by the infinity norm, I mean the supremum norm of this is the supremum of the values of the function T over the interval Ti to Ti minus 1. Okay?
Yes.
So it's the supremum of the values of the T actually in the appropriate interval A to B, for example. Okay? So this is just one value. So this must be less than or equal to the supremum. So you should have it. Okay? And now this is a fixed number. Okay? So you can take it out. And once you take it out,
Limit
and have it square as well. So what I just want to do is that I want to make sure that this goes to 0. That's what I want. So I'm going to have f of, okay, so I'm playing a trick, trying to make sense of it yourself. So I'm just pulling this out, and Ti to Ti minus 1, I'm estimating this difference by the norm of delta n. And I want to keep one Ti to Ti minus 1 in the expression I equal to 1. Okay? So I can square here. Okay? So I can write this as a Ti minus 1 multiplied by Ti minus 1. So obviously I know that Ti minus 1 is less than or equal to the maximum because this is the maximum, okay, of the length of all subintervals. And this would be what? This would be f prime of infinity of n and v minus a. So that's it. What do you call Riemann sum? And this would go to 0 as this guy goes to 0. Okay. So that's if you have differentiability, you have it. Still, this integral of f with respect to f makes sense. So one, it has quadratic variation, it makes sense. Other, you have differentiability. But differentiability is of no use of us actually. Because the things, the creatures, the species that we are going to talk about, they are not differentiable at all. Okay?
This is not any users.
Okay? So, but okay, here's the thing. Our random processes are not differentiable. Okay? This is not interesting for us. But what I'm going to show that you can have random processes which are continuous and has this property that their quadratic variation goes to 0. Okay? One of the key things that we have to keep in mind. I have assumed that f is continuous from A to B. Okay? Whenever, so one of the biggest misconceptions that we have in our head, so whenever we think of continuous, we think of this. Okay? So if I say you draw a continuous curve for me, the people are, 99% of the people are going to draw this. No one is going to draw this. Well, that's continuous too actually.
Not differentiable.
But it's not differentiable. So this is not a good example of continuity. That's an example of differentiable function. So what I'm saying that I can have some functions which are wiggly, in other words, random in its nature, and they are continuous, and their quadratic variations are 0. Hence, at least for those random processes, the integral of the random process with respect to the itself makes sense. At least for those random processes for which the trajectories are continuous and they have this quadratic variation property, okay, you have the Riemann Stieltjes work actually. Okay? But trouble is the randomness is nasty. It's not always necessarily going to have these nice properties. Though the kind of processes that we are going to deal with, as a key example, for example, the Brownian motion. So the Brownian motion has both of these properties. Okay? So it has quadratic variations and it's continuous. Okay? But still this is not going to help. Okay, so so imagine I have Brownian motion which has quadratic variation and continuity. So only this definition allows you is to define the integral of Brownian motion with respect to itself. Okay? But the more interesting question would be, can I define the integral of the function of Brownian motion with respect to the Brownian motion? Again, what kind of properties this function should have so that this makes sense? Okay, so it's a beautiful theory, You ask a lot of questions, you extend your intellectual intuition, and you try to do some of the really impossible things actually. You have to do it.